So let's go back all the way back to 11.1, inverse variation. This is the first section of a chapter, and talk about what we call about the inverse variation. Okay. Before we even start with that, I'd like to remind you of what a constant of variation is, because this is the key to the problem, and you have to understand that whenever we talk about constant of something, that particular value will tend to stay the same throughout the problem. It will not change at all. Whatever can change, but the constant itself will never change. So let's kind of put you into a real life context here and see if you can actually figure out which one is the constant of variation. Let's recall this particular formula, d equals r times t. We use this a lot. Distance equals rate times time. I know that some can argue that certain things can stay the same. It could be true, but let me just give you this problem. Pretend that you are driving from San Jose all the way to Los Angeles. Okay. Typically, it will take you about 6 hours to drive there, but the time can change. Is that true? Depending on how fast you drive. If you drive fast enough, you can actually cut it down to about 5 hours or whatever. And if you drive slower, it can take more than 6 hours. Okay. The only thing that's being constant here that will never change is the actual distance from San Jose to LA itself. And as you know, it's always going to be approximately 400 miles apart. You cannot physically take San Jose and move it closer to LA, right? So therefore, the thing that's being constant is the distance. So we can call this and label this as our constant of variation. It will never change no matter what. Okay, pardon my writing there. And the only thing that the only two that can change is the rate and the time, because what's happening is if you increase your speed, then logically it will take you less time to travel. Likewise, if you decrease your speed, then it will take you more time to travel at the same exact distance. And you can see that if one goes up, the other one goes down, and if the other one goes down, the other one goes up. And hence, we have this term called inverse variation. Okay, variation. Okay, so I want you to take a look at what's happening here. Constant of variation is not always given to you, and sometimes you do have to find a constant of variation. And to find a constant of variation, all that you have to do is take the product of the two values that's being changed, that could change. They will never stay constants. Okay, so I can give you different problems. All you have to figure out is, well, whether or not that value is going to stay the same throughout. If it does not stay the same, it's not a constant of variation. Okay, let's take a look at this first problem that I want to give you here. And let's read this. It says if y varies inversely as x, and this is just how we indicate that this is an inverse variation problem. This is how we would say it. If y varies inversely as x, another way to say it is it's going to say y is inversely proportional to x. Okay, just another way to say it. If you hear the words inversely proportional, it also means varies inversely as x. It's the same thing. But it says y varies inversely as x, so x and y, they're not constant. They're constantly changing. So here's the first scenario. If y is 4, x is 8. Okay, and then it's asking you, well, what if x is -2? It's changed to -2. Then what is my new value for y? But for us to figure that out, we had to find out, well, where is my constant of variation? Because according to the formula that we agreed before, remember d equals rt and d is our constant of variations, we have to take the product of the two values that's being changed. In this case, the two values being changed is the x and the y. So to find a constant variation, really, all you have to do is take the y times the x. So 4 times -8 will give you -32. And to be formal about it, we use the letter k for constant of variation. Okay, so k is x times y. So we have our constant of variations to be -32. So -32 is what we want. It will stay the same throughout. So if we change it, whether we change x or y, it will have to accommodate somehow to make that value stays the same. So now it says, what if the x is now -2? What do you think y will have to be so that it will still keep the value of -32? Well, let's plug it back in. You see it? I'm using the same formula I use the constant of variation, I just found it to be negative 32, so I plug it in. So this will stay the same. Now I'm using, okay, what if x is negative 2? What does y have to be? So let's solve for y. If I divide by negative 2, as you can see, it's going to become 16. So that means my y is 16. Okay? That's how we find our missing values. Likewise, for this particular problem right here, let's take a look at this. It says, as the temperature increases, the level of water in the river decreases. When the temperature was 90 degrees Fahrenheit, the water level was 11 feet. So let's kind of take notes on that one. 90 degree Fahrenheit. The level of water is 11 feet. Okay. So as it gets hotter, what will happen to the temperature, as you can see? Well, if you know anything about evaporations, if the temperature gets hotter, more water will be evaporated, and so the level of the river will go down. So if this increases, the level of water will go down. Okay, that's what you expect to have. So since these two are being changed, or not being constant, we don't have the constant of variation, do we? All they have to do is find it is to get the product of the two, and you can see it's going to become 990, and this is our constant of variation. And remember our formula to find it is just going to be k equal x times y. These two are being changed. Constant of variation is going to be the same, so I'm going to use 990 to plug into place of k. And in this case, it doesn't matter which one you call x or y. So let's call this x, this is y. Then x can be 110, and y is what you want to find out, the level of the river, divided by 110. Then y is going to become just 9 feet. Okay, so that's my answer for it. And it makes sense too. The hotter the temperature, the lower the river level. Okay, so to kind of finish it off here, I want to finish with a review with you for this entire chapter. So let's take a look at this problem. I have 3x over x squared plus 3x plus 2 minus 3x minus 6 x squared plus 4x plus 4. Notice I put in extra parentheses to kind of remind you that this is a group of its own, equal to 0. So it has a lot of things involved in this problem. It has different denominators. It has, things can be factorable. Set it into an equals, this rational equation as well. So the first and foremost always is, if it's factorable, whether it's you can take out the GCF or whatever, please take it out. So 3x, I can't do anything about it. This one, however, I recognize that it's not a PST, but it's a trinomial. Perhaps I should use the x, but not the box, because this is a 1. I don't need a box for it. Although if you want to go and do the box yourself, you can certainly get the same answer. So with this one right there, if you use the x, it's going to be 2 on top is 2 times 1, 3 in the bottom. So the factor is going to be 2 times 1, I give you 2. 2 plus 1 is 3. So I can write it as 2x plus 2, x plus 1. Over here, I can certainly take out, I know the general habit is I want to factor the best I can, right? So let's factor anyway. Here's the 3, and I can take out the 3. Then it's going to be 3 equals times x minus 2. Down here, I can also use the x, or if you recognize it to be a PST, which it is, you can also use the PST ways if you want, but I want to show you that the x also works. 4, 4, 2, 2, right? So that's going to give you x plus 2, x plus 2, everything equals to 0. And for the sake of fraction, I'm going to put a 1 underneath it to complete it. Okay? And move on here. Since we don't have the common denominator, we have to quickly find our denominators. Let's find it. First time seeing x plus 2, so I'm going to put that into my toolbox. I'm going to put it every place. First time seeing x plus 1 as well, I'm going to place it in as well because I need to unlock it. Okay, and over here I already have x plus 2. However, I also find that there is another x plus 2. I don't have enough of x plus 2, so I also need to include another x plus 2 down here. Okay, now last step is to compare. What's missing? In this case, I have x plus 1, x plus 2, but I'm missing another x plus 2, so I'm going to move that to the top. So I end up with 3x times x plus 2. Here I have 2 of x plus 2 already. What I'm missing is the x plus 1, so I'm going to move that to the top. Here's x plus x plus 1. Here I'm missing everything. However, when I move to the top, there's a 0 on top. So 0 times anything is always 0. You see it? And as you know, I mentioned this before in class, that once you have your numerator established, you can certainly cancel out your denominator. Okay, we're technically clearing fractions anyway. And of course, you can distribute, do the FOIL over here, first, inner, outer, last, to combine like terms together. So this becomes 3x squared plus 6x. This one, let's do the FOIL first before I distribute a negative 3. So it's going to be x squared. This is plus x. This is negative 2x. This is negative 2 equals to 0. Okay, and then I can certainly distribute a negative 3 into each one now. And that becomes negative 3x squared minus 3x plus 6x plus 6 equals to 0. And see if I can combine like terms. Oops, there it is. I have 3x squared canceled. I have, oh, I missed the x. 6x, negative 3x, so that becomes 3x plus 6x, that's 9x, plus 6 equal to 0. Subtract 6 both sides, so 9x equals to negative 6. And as I kind of move up here, divided by 9 both sides, I will have negative 6, 9, or you'd reduce that to negative 2/3, okay, as your solution. And before you even conclude it, highly suggested you plug it back in the test. But for the sake of review here, I want to remind you about our excluded value. Notice that I have different factors here, right? So in this case, if we're looking for excluded value, this cannot be 0, this cannot be 0, okay? So therefore, if you solve for it, x cannot be 2, right? So that's one of our excluded value. Over here, x cannot be negative 1. So this is also our excluded value, okay? Okay, excluded value, we've talked about this excluded value before, where the denominator cannot be a 0. So to make the 0, x is going to be negative 2. To make the 0, x is going to be negative 1. So these two cannot be included as our parts of solutions. And we talked about this before, and it doesn't hurt for you to, at the very end, plug it back in and test it to make sure everything works out just fine. But ideally, this is our final answer with 2 excluded values. And that's going to kind of wrap up our chapter 11. Any questions on this? Feel free to come back with questions on Monday.